Welcome to Chem Talk, where we discuss chemistry. Today we are looking at valence electrons and electron configuration.
Yeah, these two topics are, well, they're absolutely fundamental. If you really want to get why atoms do what they do, why they bond, react, or sometimes just ignore each other completely, you have to understand these ideas.
Right, and we're not just here to throw jargon around. The goal is to dig into why this stuff matters, get those key insights that explain the basic rules for how atoms interact.
Exactly. Think of it like this. We're figuring out the atom's sort of social profile with valence electrons, and then we're looking up its internal address book with electron configuration.
Okay, I like that. So we'll unpack valence electrons, then electron configuration, and touch on those key rules. The Aufbau principle, Pauli exclusion principle, and Hund's rule. Sound good?
Sounds great. Let's start with maybe the most crucial part, valence electrons.
All right, valence electrons, often called VEs.
Yeah.
What there? Exactly.
Simply put, they're the electrons in the outermost electron shell of an atom. That's the shell with the highest energy level. And these few electrons, they pretty much define the atom's chemical personality.
Okay. Outermost shell. I've heard the Russian stacking doll analogy used here.
Yeah, it's a decent one. The nucleus is tiny, right in the center, positively charged. Then you have shells of electrons layered around it, like the dolls. The biggest outermost doll holds those valence electrons.
And being on the outside is really important, isn't it?
It's everything. Because they're farthest from the positive pull of the nucleus, they feel the weakest attraction. There's this thing called shielding.
Shielding, meaning the inner electrons sort of block the nucleus's positive charge.
Exactly. The inner electrons get in the way, absorbing some of that pull. So the valence electrons only feel a weaker, effective nuclear charge. It's like the nucleus's influence is diluted by the time it reaches the outer shell.
So wait, if the pull is so weak out there, why don't they just drift away? What keeps them attached?
Ugh, good question. It's a balance, right? The pull is weaker, but it's still there. It's strong enough to keep them part of the atom under normal conditions. But it's also weak enough that it doesn't take a huge amount of energy, maybe from another atom bumping into it, or just thermal energy to get them involved in interactions. It can be shared or even transferred entirely.
Okay, so they're easily accessible for chemical reactions. That makes sense. What drives them? What are they trying to achieve in these reactions?
Stability, that's the name of the game. For most atoms, especially the main group ones, stability means getting a full outer shell, usually 8 valence electrons. We call that the octet rule.
The octet rule, like trying to be like the noble gases, neon or argon. They're stable because they already have 8.
Precisely. They've achieved, atomic contentment, so other atoms react to try and get that same stable electron arrangement.
So back to the personality profile idea. An atom with just one valence electron, like sodium, it's desperate to lose it, right? To expose the full shell underneath.
Absolutely. Very reactive. And an atom with 7 VEs, like chlorine, it's just as desperate, but to gain one more electron to complete its octet, also very reactive.
But if an atom already has 8 V's, like neon,
It's stable, happy as it is, chemically inert mostly, doesn't need to react.
and the amazing thing is, we don't need complex calculations to figure this out for many elements. The periodic table gives us a massive shortcut.
It really does. It's organized by chemical properties, which directly relates to valence electrons. Elements in the same vertical column, the same group, have the same number of valence electrons.
So for the main group elements, those taller columns, groups 1 and 2 and 13 through 18, how does that work?
Super easy. For group 1, like lithium or sodium, they have 1 VE. Group 2, like calcium or magnesium, they have 2 VEs. The group number tells you directly.
Okay, and for the other side, groups 13 to 18.
Just subtract 10 from the group number, or even easier, just look at the last digit of the group number. Group 16, like oxygen, it has 6 VEs. Group 17, the halogens, 7 VEs. Group 18, noble gases, 8 VEs, the stable octet.
That's incredibly useful. So just by looking at its position, an element's main chemical motivation.
Yeah. It tells you its identity, its likely reactivity. But to get the full picture, we need more detail than just the outer electrons. We need to know where all the electrons are.
Which brings us to electron configuration, the atom's address book.
Exactly. Electron configuration is the specific, formal way we write down the arrangement of every electron in an atom. It tells us the energy level, the type of orbital, and how many electrons are in each spot.
So it's like city, energy level, street, sublevel, type S, PD, F, and house number, electron count.
That's a pretty good analogy, yeah. And because electrons always want to be in the lowest energy state possible, there are rules for how they fill up these addresses. 3 key principles govern this.
Let's start with the first one, the Aufbau principle. Sounds German.
It is. It means building up. And the rule is simple. Electrons fill the lowest available energy orbitals first before moving to higher energy ones.
It's like filling up the ground floor of a parking garage before going to the second floor.
Pretty much. But here's where it gets interesting. The energy levels aren't always strictly sequential by the main number, like 1, 2, 3. Remember how we fill orbitals? It goes $1, then $2, 2 per 2, 3 pilas, $3, but then $4 comes before $3.
Right. That always seemed weird. Why jump to level 4 before finishing level 3?
It comes down to the complex interplay of energy levels and orbital shapes and how electrons shield each other. The source orbitals are spherical and penetrate closer to the nucleus than the d orbitals of the previous energy level. So even though $4 has a higher principal number, 4 versus 3, its shape allows it to sneak in closer to the nucleus, feel a bit more pull, and actually end up being slightly lower in energy than the $3 orbitals.
Ah, okay. So it's energetically cheaper for the electron to go into $4 first, even though it feels like skipping ahead.
Exactly. It's the lowest energy path available at that point.
Wow.
Nature takes the cheapest route. Understanding that overlap is crucial, especially for transition metals.
Okay, so Aufbau tells us the filling order. What about capacity? How many electrons can fit in one specific orbital, like one of those bio-orbitals?
That's the Pauli exclusion principle. It states 2 things. First, a maximum of 2 electrons can occupy any single atomic orbital.
Only 2 per orbital. Got it. And the second part?
Those 2 electrons must have opposite spins. We usually represent spin as up or down. Think of it like a fundamental property of the electron.
So they can share the same energy level, the same sublevel type, like P, and even the same specific orbital, like the Puig orbital, but they have to differ in their spin.
Correct. No 2 electrons in an atom can have the exact same set of 4 quantum numbers, which include energy level, sublevel, specific orbital, and spin. The opposite spins allow them to occupy that same tiny space without repelling each other quite so strongly, like 2 dancers spinning opposite ways in a small area.
Make sense? 2 down, 1 principle to go. What happens when you have multiple orbitals with the exact same energy, like the 3 p orbitals, ppx, p, z, z, in a given shell?
Ah, that's where Hund's rule comes in. This one's about minimizing repulsion again. Hund's rule states that when filling orbitals of equal energy, we call them degenerate orbitals, electrons will occupy each orbital singly first, before any orbital gets a second electron. And importantly, all the electrons in the singly occupied orbitals must have the same spin, parallel spin.
The bus passenger rule, right? People take an empty seat by themselves before they sit next to a stranger.
Exactly. Electrons are negatively charged, they repel each other. By spreading out into separate orbitals first, they maximize their distance, which minimizes repulsion and leads to a more stable, lower energy arrangement. They keep the same spin while they're spread out.
So take nitrogen. It has 7 electrons. Its configuration ends in 2p33. How do those 3 electrons arrange themselves?
According to Hund's rule, you'd put 1 electron in the 2px orbital, 1 in the 2p-px1, and 1 in the 2pss. All 3 would have the same spin, say spin up. Only if you added a 4th electron, like in oxygen, 2b4-4 would you then start pairing them up, putting a second electron with opposite spin into one of those orbitals.
Okay, Aufbau for order, Pauli for capacity and spin, Hund for filling equal energy orbitals. Those 3 rules map everything out.
They do. And now we can use this configuration to understand real chemical behavior. Let's go back to sodium, no?
Okay, sodium. We said it has 1 Be. Its full configuration is 122, S22, P63, S101 games.
Right. That 3s101 electron is the valence electron. It's sitting out there, loosely held, heavily shielded by all the inner electrons. 1 molar P 100 of 3p.
And it wants to leave to achieve stability.
Exactly. So when sodium reacts, it readily loses that 3s101 electron. What's left? The text plus 8 corny dollars. Its configuration is now 11122s22p670. Look at that outer shell, 222p66. That's 8 electrons.
It achieved the stable electron configuration of neon.
Precisely, and losing that entire outer shell also makes the ion much smaller than the original atom. The radius shrinks considerably.
That makes sense. The configuration change directly impacts physical properties like size. What about something like magnetism? You mentioned that earlier.
Yes, let's look at oxygen. Configuration ends in 2p44. Remember Hund's rule?
Yeah, fill singly first. So the 3p orbitals get 1 electron each, all spin up, then the 4th electron pairs up in one of them, spin down.
Correct. So how many unpaired electrons does oxygen have in its 2po2 orbitals?
There were 3 singles, then 1 got paired, so 2 orbitals still have just 1 unpaired electron each.
Exactly. And the presence of unpaired electrons is what causes a substance to be paramagnetic, weakly attracted to a magnetic field. So just by applying Hund's rule to the configuration, we predicted oxygen's magnetic property. You can't get that just from knowing it has 6 VEs.
That's really powerful. Okay, let's connect it back to reactivity with those neighbors, potassium K and calcium K.
Right, side by side on the periodic table. Potassium is group 1. Its configuration ends in 4 cephalondollars, 1 valence electron.
Calcium group 2 ends in 4 sesta 2 valence electrons.
Potassium, our 4Sev11, needs to lose just that 1 electron to get to the stable argon configuration. Calcium, our 4Sesto2L2, needs to lose 2.
Losing 2 electrons takes more energy than losing 1.
Right. Generally, yes. And also, in calcium, the nucleus has a slightly stronger positive charge, 1 more proton than potassium, pulling on those 2 electrons in the same $4 Eller. So each electron in calcium's $4 orbital is held a bit more tightly than the single $4 electron in potassium.
So potassium loses its electron more easily. It's more reactive.
That's exactly what we see. Potassium reacts much more vigorously, say, with water, than calcium does. That slight difference, 1 versus 2 valence electrons, dictated by the configuration, leads to dramatically different chemical behavior. It really highlights how VEs define that atomic identity.
Wow. Okay, so wrapping this up, it seems like chemistry isn't just random chaos. There were these underlying rules.
Definitely. Valence electrons tell you the atom's main goal, its personality, its drive to react, and electron configuration, using Aufbau, Pauli, and Hund's rules, gives you the precise map of how the electrons arrange themselves to achieve the most stable state possible.
And listeners, you can use that group number trick right now. Look at any main group element on the periodic table, figure out its valence electrons, and you've got a good idea of how it wants to behave chemically.
It's your quick guide to reactivity.
So here's something to think about. We've talked about these 3 basic rules. Fill lowest energy first, max 2 per orbital with opposite spins, spread out before pairing up. How is it that just understanding these simple principles allows chemists to predict incredibly complex things, like the bonding, the color, the stability, essentially the behavior of every element?
It all comes back to electrons finding their lowest energy, most stable place. It's fundamental.
It really is. And thank you to the Geeky Gamer Science teacher for creating this deep dive.